Okay, thank you very much, Federico, for the introduction and for the opportunity to speak here. It's a great pleasure. So what I'm going to say today, it's joint work with, most of it is a joint work with Kai-Shu, and then if I have time, I will say something about joint work with Marco Pozzetta as well. So, I'm going to talk about curvature bounded below. So let's first maybe start with some recalling definitions on curvature. Okay. So I guess most of you, some of you might know some of these definitions, but my setting will be that of Riemannian manifold that will be always complete. And but how do you, I mean, the notion of curvature I will be interested in are Ricci curvature and scalar curvature. So what is Ricci curvature? Ricci is a tensor, it's a symmetric tensor on the tangent space. So let's fix an orthonormal basis, 1, 2, n in the tangent, and Ricci at the point P in the direction EI. EI is the sum of the sectional curvature of the surfaces spanned by the two planes containing I. Okay, so this one is an orthonormal frame around P. So this one is what I call sectional curvature. So to think about this object, you can think about the plane, I don't know, E1, E2, and then consider the surface issued by the curves that are tangent to vectors in this plane. This is a two-dimensional surface. Let's say we can compute its sectional curvature in the classical sense, and then we sum over all the directions that contain, or the two planes that contain EI. Okay.
You take the geodesics, right?
Geodesics, yeah. You need geodesics. Yeah, exactly. And so it's an average of sectional curvatures, depending on the direction. And then we have the scalar curvature. It's the trace of Ricci. So having a bound below, having a bound below the sectional curvature implies having a bound below Ricci, implies having a bound below the scalar curvature, but the other way around is usually false. I will be interested in this most of the time. Okay, so this is the sectional curvature, Ricci curvature, and scalar curvature. Most of the things that I'm going to say today fit in a framework of comparison geometry. The philosophy of comparison geometry is, well, you have a curvature lower bounds or a curvature upper bound, and then you want to find constraints on some geometric or topological quantities with respect to the model that attains the lower bound. What are the models? Well, there are only up to scaling 3 models of constant curvature that we should have in mind that are simply connected. It's the sphere, okay, and this is the unit sphere in Rn+1. This has constant sectional curvature 1, which means that at every point and in every direction, Ricci is n-1, because you sum n-1 of them. Then you have the flat space Rn, in which sectional curvature is 0 and Ricci is constantly equal to 0. And then we have the hyperbolic space, which I don't know how to draw exactly. Imagine like a hyperbolic surface, okay? And here the sectional curvature is -1 and Ricci is -1. So the idea of comparison geometry is like proving or understanding theorems that look like you have a manifold on which your curvature is bounded below or above by one of these models, whatever curvature you know. Of course, you can put also scalar here. Let me just put this. Computation is similar here. So you have a theorem that's like, okay, if your curvature is bounded below or above by the one of the model, then the diameter, the volume, the topology, whatever, is bounded in some sense by the one of the models. So arguably one of the most classical results in this line of research is Bishop-Gromov and Bonnet-Meyer's theorem. So the story, I try to reconstruct the story of this theorem. Let me see. So first of all, you start with a complete Riemannian manifold. And you assume that the Ricci curvature is bounded from below by the one of the sphere, which with this, I mean that at every point, testing against every unit vector, you have that Ricci is greater or equal than n minus 1. Okay, then, well, intuitively, you have a manifold that is positively curved, and you want to show that it closes up within a certain amount of time, okay? And this is what happens. The diameter is less than pi, and pi is the diameter of the sphere, of the unit sphere with the intrinsic metric in n plus 1, okay? So this is sharp. So this was proved in 2 dimensions for the first time by Bonnet in 1855 for surfaces. Then the generalization is due to Myers in this classical version here in 1941. Then, well, not only you have the diameter is constrained, it's bounded above, you have to close up within pi, you also have that the volume cannot be too large, okay? The volume of the manifold is less than the volume of the sun, okay? And also this, of course, is sharp, because the equality you have here when you are at the sphere, which satisfies this inequality. Well, finally, as a consequence, oh, sorry, I forgot to say, this volume bound here is due originally to Bishop in 1963. And then, well, since this comes from monotonicity formula, then the full monotonicity formula is due to Gromov that realized that you have full monotonicity. Yeah, I'm hiding this a little bit here. But as a consequence, the manifold is compact, but also every universal cover is compact because this condition is preserved in universal cover. And then the pi1 is finite. So as a direct consequence of these two statements, you get that the pi1 is finite. And the qualities are sharp and rigid. By rigid, I mean that then if you have equality, then you are isometric to Sn. So this is the prototypical, if not the most classical theorem in comparison geometry. This is where I want to start a little bit my investigation, because I mean, in my work with Kai-Shu, and then in subsequent works with Marco Pozzetta as well, we try to understand how to generalize this theorem, and what can we say when we have a less pointwise but more global condition. I will try also to explain what are the motivations for generalizing this.
Can I ask a question?
Yeah.
I mean, I've seen this theorem a lot of times, but I don't really know much about algebraic geometry. But what this P1 is clear, but what about other topological invariants of the manifold? Why people don't care about? I don't know. Is it P by K or?
I mean, there are results. I mean, I think there are results on
Is there any of these results which is a direct consequence of this theorem, like the pi1, the direct consequence of this, the first 2 points.
I mean, yeah, this for the pi1. For general, I don't know if there is like a direct like if you can prove something geometric and then a direct consequence. In that case, you have to prove maybe something about bound on area minimizers in homology classes.
Okay.
But I mean, I know there are well, when the sectional curvature is positive or negative, there are theorems also on Betti estimates on Betti numbers, something like that.
Okay. There's nothing simple that one can say already.
Yeah, no. From this, like, I don't. Yeah. I don't think there is. Just a curiosity. Yeah, no. Yeah. Other questions?
Sorry, yes. Algebraic topology, not
Yeah, you said algebraic geometry. I was like, oh, what's going on? It's okay. It's okay. Well, one obvious way you can start to think about generalization of this is what happens if instead of having a lower bound on Ricci, you ask for a lower bound on scalar curvature, okay? So, try that. To generalize. So, what if you have scalar curvature uniformly positive? So, do you see if there is any of these that fail? There is one that fails almost in well, all of them. But you have ways to construct in an easy way something that is non-compact but with uniformly positive scalar curvature. You can take R cross S2. This is uniformly positive scalar curvature, and the diameter is bounded and the volume is unbounded. So you have no ways to try to constrain like the diameter in such an easy way. But here maybe, I mean, you can't make this example too large depending on the scalar curvature lower bounds, because then this one is telling you how big or small you can take the sphere. So maybe you can prove something like, oh, the sections of my manifolds or area minimizers behave well. And this is something that appeared for the first time in, as far as I know, in work of Shen and Yao, and also Gromov and Lawson in 1983, where they start to study manifold with a positive scalar curvature lower bound, and then they prove this proposition that tells you that if sigma 2 in M3, so is minimal and stable, so I will say what it means. This is a condition that is implied by area minimizing. Then, having a scalar curvature lower bound on the three-dimensional manifold will give you a strange curvature lower bound on the minimal and stable hypersurface, which is no more pointwise, but is spectral. So now you can see this is a Gaussian curvature, which is a function on the surface. This is a Schrödinger operator, okay, the taxon functions. The first eigenvalue of this operator is positive. So maybe the curvature is not positive, but the first eigenvalue of this operator is positive. This is a consequence of basically Gauss equation and minimal and stable condition.
Greater or equal than 1.
Mm-hmm.
And k is a function that depends on the pointer.
Mm-hmm. This means the integral of grad phi square plus chi phi square for every I c infinity k c. So of course, if you don't have this contribution, then this is a scalar a sectional curvature lower bound, and then you can apply the theory. But now, I mean, one motivation to understand spectral curvature also comes from this. If you want to generalize things with scalar curvature lower bound instead of Ricci curvature lower bound, you end up seeing a spectral curvature condition on top of area minimizers in manifolds that have curvature lower bounds. So the heuristics, the general heuristics, seems to be.
So K sigma squared is the scalar curvature of sigma, right?
Yeah. Scalar curvature,
Your
Gaussian
sigma-
curvature. Yeah, it's everything is two-dimensional here.
Yeah.
So yeah, exactly. So also, I mean, also the Schrödinger operator with the scalar curvature is often studied when you try to find conformal metrics that are positively scalar curved. And anyway, the heuristics is that if you have some kind of lower bound on some notion of curvature on the larger ambient manifold, you expect to get a slightly different but spectral lower bound on top of stable minimal hypersurfaces. Of course, I mean, this is just a nonsensical statement. What I'm telling you is that in 3 dimensions, scalar curvature here implies spectral sectional curvature. And well, in general, if you twist a little bit the curvature here, you might end up with a different notion of curvature. And you see this appearing in the Gauss equation. So you have to inspect the Gauss equation and understand what's going on. So also because of this, I mean, I started to be interested, and other people got interested in understanding what happens to the geometry and the topology of manifolds that have a curvature lower bounded in a spectral sense. I'm not claiming it's new, it has been going on for many, many years. In particular, I got interested with my collaborators on understanding manifolds with spectral Ricci lower bounded. So let me introduce what this means. Okay. So now Ricci from now on is no more a tensor, it's a function, and it's the pointwise lowest eigenvalue of the Ricci curvature. So from now on, think about this is the lowest eigenvalue of the Ricci tensor. So now Ricci is a function that pointwise it's just the lowest eigenvalue. Of course, I mean, if this is consistent with writing Ricci greater or equal than n-1, and now we can understand this as a function greater or equal. Given 2 numbers, gamma and lambda, I say that minus gamma delta plus Ricci is greater or equal to the lambda if the first eigenvalue of this Schrödinger operator is greater or equal than lambda. And this can be stated in a functional analytic way. Okay. And this is the condition I'm interested in now. You can, working backward from the heuristics, you can ask yourself what is the right notion of curvature on the ambient manifold that gives rise to spectral Ricci lower bound on the stable minimal hypersurface, and it turned out to be a lower bound on a so-called bi-Ricci curvature. It's the bi-Ricci tensor is just you sum the 2 lines, the sectional curvature containing U and V. And if you have that bi-Ricci split in lambda, and
What's the last term?
oh, sorry, K UV. is the sectional curvature of the two planes.
Of the two planes.
Of the two planes. So what you're doing, you're summing the first two rows in the sectional curvature. What?
So there is a minus in between.
Ah, yeah, there is a minus. Yeah. I didn't want to introduce a lot about this.
So this is equivalent to sum over all pairs of planes which contain.
No, it's this. If I don't know if you have E1 yen, E1 yen, this is the sum of the sectional curvature here.
Yeah,
This
okay.
plus this minus, right? It's the sum of the upper diagonal entries in the sectional curvature matrix is the first two entries. So you can, so if you do these on all the row, you get a scalar curvature. If you do this on the first, you have Ricci. So you can now you can also think about an interpolation of curvature lower bounds. Yeah, I mean, I want to. So this one is the one after Ricci, is by Ricci, and the idea is that the one after will imply spectral Ricci lower bound, spectral lower bound, the one before.
Ah,
Yeah, kind of up to some dimension. There is a bound of the dimension, so that I would neglect it, or maybe not. But sure, in low dimensions. But this is true in every dimension, actually, if this is stable and big enough. So the condition that I'm interested in, following these heuristics, it comes from a lower bound on a Ricci curvature on the manifold, which you can understand as the first step interpolation from a Ricci lower bound to a scalar curvature.
so in particular, also if I only have Ricci, but Ricci greater or equal than lambda, then I have this.
Yeah, you have to
Up to
change the
one
constant.
constant,
Yeah. Yes, indeed. Oh, no. Because here you are not summing this. No.
Ah, so it's not entirely true that it's like, because if I have Ricci greater or equal than something, then this implies something on scalar.
Yeah.
But it's not true in.
No. Because when you sum all of them, then you have the double. But this is not, it's an interpolation, but it's not an implication. Okay, so this is the notion I'm interested in, which is somehow motivated by this kind of observation. And if you want to go back, this is the notion on the ambient manifold I'm interested in, because you get spectral Ricci lower bound on top of this.
Is it equivalent to say that the sum of the two lowest eigenvalues of the Ricci is bigger or equal than lambda? Or not?
I don't think
not
so.
really.
I don't think so, because there is
Because there is that one missing.
There is this missing one. Yeah. This plays a role when you do the second variation. The things that misses is so. I mean, it allows you to show this inequality. But yeah, so now I'm gonna go on and study this. The motivation is this. Let me tell you one more word why I got interested in studying the manifolds like this per se. First of all, because they offer a generalization to classical result of Bishop-Gromov, which I think is appealing per se. Second of all, because they come as on top of stable minimal hypersurfaces in manifold with this Ricci curvature, and this was this circle of ideas was recently used to prove that stable minimal hypersurfaces in R5 and R6 are actually hyperplanes. This is a contribution of Chodosh, Lee, Minter, and Stryker in R5, and in R6 it's a contribution of Mazet. So these observation that unstable minimal hypersurface by Ricci comes to spectral Ricci, and the study of geometry of manifolds with this condition played a role in the recent proofs of the solution of the stable Bernstein problem. But yeah, I don't want to dive into these details. Do you have any questions? So after all these detour, I think I owe you a statement. So this was just to motivate why one would be interested in finding spectral Ricci lower bounds. And how much time do I have?
Half an hour in total, you should stop in 25 minutes.
Yeah, just another thing that I wanted to mention en passant is that there are other notions of curvature that eventually implies a spectral Ricci curvature lower bound. Some LP control on Ricci for P large enough will also imply spectral control on Ricci. So there are several ways one can get interested in trying to understand spectral Ricci curvature and trying to generalize theorems like this. So I forgot, I lost count of maybe 5. Spectral Bishop-Gromov. So we got interested in understanding spectral Ricci curvature lower bounds, and I'm telling you that we can basically generalize. Let me start with the volume part of this theorem, asking less. But before doing this, one simple remark about the spectral condition. Well, of course, if gamma is greater or equal to 0, then Ricci greater or equal than lambda implies this, because minus Laplacian is a positive operator, and well, if you just look at the definition, this will be positive. So you're just adding a positive term. One useful example to have in mind that makes false the opposite implication is the hyperbolic plane. So in Hn, the first eigenvalue of the Laplacian, minus Laplacian, which is the positive operator, is n minus 1 squared divided by 4. There is a spectral gap. So this now tells you that if you give enough power to minus Laplacian, the hyperbolic plane, the hyperbolic space in general, becomes non-negative or even positively Ricci, spectrally Ricci curve. Indeed, as a function, the lowest eigenvalue of the Ricci tensor is minus n minus 1, so you can make some computations and find that if gamma is greater or equal than 4 divided by n minus 1, or even if it's strictly greater, then you have greater or equal, because this basically gives an estimate on this term. So now we have a clear enemy, a clear non-compact enemy that you should be aware of if you want to generalize this kind of theorems to the spectrally positive Ricci curve case. Because if gamma is large enough, then the hyperbolic space, which is non-compact, becomes positively spectrally Ricci curved. So this is something that we should be aware of, and it will probably result in asking compactness in generalization of this theorem, depending on gamma, okay? And also shows you that you can't go the other way around in this implication, but this was kind of maybe clear and unexpected if it were to happen. So now we have the theorem. This is theorem I put with Kai last year. And well, let's take a compact. Let me discuss compactness in a moment. Riemann manifold. and assume n greater or equal than 3. The case of surfaces can be discussed separately. It's not the point. Assume spectral generalization of this condition. So it's basically exactly. So I mean, if there is not this term, you have Ricci greater or equal than n-1. Here, you are weakening this condition. Okay. Then, well, what is interesting that we found interesting is that 2 and 3 holds in the same way. Okay. So then the volume is less than the volume of the sphere, and pi1 is fine. Now there are several things to discuss here. So this is a spectral generalization of the Bishop-Gromov theorem, but there are several things to discuss here. Equality case actually is rigid, okay? Equality in one is rigid in the sense that if I have this condition and I have equality here, then I'm isometric to the round sphere. And this number here is optimal. Okay. So you can't ask for a better gamma here. Also, n-1 divided by n-2 is optimal. In a sense that for every gamma greater than this number, I can find a compact manifold with dimension n greater or equal than 3, which satisfies this condition, and for which I have like arbitrarily large volume, and the pi1 is not finite. Okay.
But this example is not that one.
No. It's not this one, because actually maybe it's important to notice that n-1 divided by n-2 is greater than 4 divided by n-1. And then actually we really need compactness here. Otherwise the rescaling of the hyperbolic space, and you rescale it a little bit, this condition is true.
So you're having a quotient of the hyperbolic space.
Yeah, quotient of the hyperbolic space.
Okay.
So you're making the claim that if I take the hyperbolic space and I rescale it, I can satisfy that one?
Yes.
But this one it's implied
Because of this.
Oh.
So you need compactness.
But what about quotient?
What about quotients? Because you say like if you take quotients of hyperbolic space,
But Ricci is pointwise, so I don't that you don't touch. I don't know what happens, but I would have thought that also spectral would work.
No. It's not true what you're saying. Like the inequality is going in the opposite direction. It's not true that that one is implying that one. Because n-1 divided by n-2 is larger. I'm putting a larger positive part, which is minus Laplacian there.
Exactly. So it's true even more for that.
So the hyperbolic space would
Satisfy.
Oh, Jesus
satisfy.
Christ.
but with the, quotient of hyperbolic spaces will not be a counter exact. So I don't know if you're asking if quotient of.
I mean, if you start making quotients, then gamma becomes larger, right?
Yeah, I think so. Yeah.
I mean, because
Right.
I mean, the scalar curvature remains the same, but the Laplacian is affected by the
Yeah,
fact
yeah,
that
yeah.
the coordinate, no? As a quadratic form.
You should be happy.
Well, then it falls into his assumption.
But then it's not true, so it cannot fall.
It should not fall into your assumption because the pi1 is not
Otherwise,
finite.
but also not the volume. You will never compare the volume.
But this one, like, it's difficult to do something for quotient of hyperbolic.
We don't know enough hyperbolic geometry.
Yeah, no. I mean, the lambda one of quotients changes. Now it should become
When it should
less.
fall into your assumption. It should become less.
becomes less. I guess the lambda one of minus delta should become less than.
Why it could be that the quotient is compact?
Yeah, but then you will never have the right volume constraint. I could take a quotient which has a huge volume. I mean, right?
Also, a compact hyperbolic surface doesn't have pi1 finite, right?
No, but even the
Right,
volume of
right,
just
right, right.
why the volume.
Totally right. Yes, yes, I understand.
So it means that he cannot satisfy.
Yeah, no, exactly.
For some
I mean,
reason,
yeah, you can't satisfy it. Now, this is a consequence of the theorem.
As I don't see why, but I believe it's because they came otherwise before.
Yeah. And I mean, and this is optimal. This is optimal. The counterexamples are actually worked product of S1 with Sn minus 1. And I can say more about this later, but okay. But this is the part of the volume. The nice part is that I don't have a clear geometric meaning of this optimality, of the optimality of this concept. It turns out that it's optimal because we can prove it with it and we can prove without it.
But one question, so if you go slightly above n-1 over n-2, but slightly below, I'm very confused as to which one is the right direction.
The condition becomes weaker if you go with a bigger gamma.
Then let's go slightly bigger. Then you have no control whatsoever. Like your volume can be as big as it wants, and
Diameter can be as you want, by one.
whereas I know the diameter even now can be.
Yeah, even now can be as big as you want. Yeah. And actually it is. Yeah, it can be.
I can.
There are examples in which you can make examples with this assumption. So there are two clear thresholds here. After this, you don't expect anything. Here, you can prove things if you are compact, and here you have here you can prove things if you can prove volume bounds if you are compact, but not a diameter bound. Here you can prove a uniform diameter bound depending only on gamma. This is the picture.
So, but presumably for the quotient of the hyperbolic manifold, you're just saying that the first eigenvalue becomes too large.
Yeah.
That's what should happen.
That's what I think it happens. Yeah. I know
But then it doesn't fit anymore into your
into this assumption.
So it becomes too small. We are small for that.
No, why? I mean, you have less functions to plug into the. You have less functions to plug into the test. No?
Okay, depends what is your Laplacian. It's a positive Laplacian, right? So the first eigenvalue is positive.
Yeah, but if you make the thing smaller, it becomes even more positive.
But then it could be.
No. It's a weaker condition if you actually put a larger. Okay, maybe I'm getting confused because
we can.
Yeah.
No, because like the first month I was making the problem with side.
Because the constant you're putting there is a constant of the reciprocal of the Laplacian.
Yeah.
Okay.
Okay. Let's not discuss the counterexamples. I want to say maybe a couple of words on the proof. And here there is, the diameter is missing. If I have time, I will say something about the diameter as well.
Can you remove this compact assumption and prove the manifold is compact?
Yes, if gamma is less than 4 divided by n-1, you can remove compactness in the state. Which means that compactness is a consequence of the condition. Sorry, gamma is this number here. You have a condition with gamma, which is strictly less than 4 divided by n-1, you actually get compactness out of it. And then you have it. And but within the range, you get the volume bound, but not the diameter bound if you have compactness. And above, you don't get anything. That's the catch. So the proof, a sketch. So actually, the idea of the proof is to follow a strategy that was devised by Hubert Bray, which gave an alternative proof of the volume comparison. So let's just focus on one. Then the pi1 finite, one should work a little bit more because when you pass to the universal cover, you might stop being compact, but you can do that. So let's see a sketch for the first property. So the idea is of Hubert Ray, his PhD thesis, 97, if I'm not wrong. And actually, in the solution of stable Bernstein problem in R5, Chodosh, Schliminter, and Stryker proved this result with n equal 3, using like twisting a little bit Bray's approach, and then we proved it in all dimension. And so let me give you an alternative proof of Bishop-Gromov theorem using the idea of Bray. So when there is no control here, so I will give an alternative proof of Ricci greater or equal than n-1 implies volume upper bound. And then I will tell you what you have to do to modify this to make it work in this case. So let's say. So if you have this, now I want to show this. The idea is to use the isoperimetric. So let me define this function, which is called usually isoperimetric profile. Okay. You take the perimeter of isoperimetric sets. With the positive Ricci curvature, you have compact, so you always, this is actually a minimum, okay? You always have isoperimetric.
So that's I of V.
Yeah, exactly. So, yes. Now, I of V is a function that begins and stops in a finite time. And this time is exactly the volume of the manifold. And you have a constraint on how it starts, because if you take small balls around the points, you will see a behavior that is Euclidean. So you have a condition on the derivative here. So what is the idea of Bray is that if you prove a concavity property of this function, then you have an upper bound on the extinction time of this function. So you have to prove a concavity property of this, okay? Which is likely sharp in the case of the sphere, you should like. And the usual way you have to prove a concavity property of the isoperimetric profile is to take an isoperimetric set and to use the information that is isoperimetric, so that is critical for volume preserving variations. And if you do the computation, this will give you a condition on the second derivative of the isoperimetric profile and the volume V of the isoperimetric. And actually you can prove that under Ricci greater or equal than n-1, you have this inequality. It seems a bit, I mean, you can rewrite this as a concavity property of the correct scaling of the isoperimetric profile. Why Ricci lower bound is important here? Because when you do the second variation in a Riemannian manifold, you see the Ricci curvature in the normal direction of the isoperimetric set. And this one is inequality on the set. Actually, a way to understand this inequality is that actually the lower bound that you have in Ricci, you will see it here. And if this is 0, then this is equivalent to saying that the correct power is concave. So it's a little bit more than than having the concavity of the correct power. But now we can use ODE comparison. You have equality here for the isoperimetric profile of the sphere. You have the correct initial condition, which matches the one of the sphere. You have the ODE inequality. Then the extinction time is less than the extinction time of the isoperimetric profile of the sphere, which is the volume of the sphere. And that's the proof. So what happens now when you have a spectral Ricci lower bound? So what we did, we tried to find the correct isoperimetric problem whose isoperimetric profile function satisfies exactly this equality, and for which we can basically apply again this idea. And our proof substitute I man with this new isoperimetric profile. Now, since you have that condition on a compact manifold, you can take one first eigenfunction up to scaling. You can fix one that has minimum one. I don't know. Okay, take minus gamma Laplacian plus u times Ricci. So you have a function like this with the minimum of u equal to 1. Take the first eigenfunction of this Schrödinger operator and you rescale it so that the minimum is 1. This is a positive function. Okay? Now you look for an isoperimetric problem which has two different weights depending.
At this point, like this inequality that you're written down, should I understand that pointwise or
Pointwise.
and u is also positive? No?
Exactly. The minimum is 1. You can do that. It's a consequence of having that control on the Schrödinger operator. And now you look for an isoperimetric problem, which is good enough to have this concavity property. We tried, and it turns out you have to separate the weights on the volume and on the perimeter. And I mean, it's not meaningful if I write it like this, but this is the and this is the isoperimetric profile. There is only one choice of exponents here that work, that make this computation work. If you now take this new weighted, unequally weighted isoperimetric profile, okay, and you run the computations, you find exactly this inequality. Now, since the minimum is 1, you are lucky because the initial condition is matching from the right side, the one of the sphere. Then you conclude by the decomparison.
So the 1 is 2 over n minus 1, and 1 is n minus 1 over n minus 2.
Yes.
So even the denominator are different.
Yeah, exactly.
Can you repeat what is a U? Sorry.
U is the first eigenfunction of the Schrödinger operator on the compact manifold, rescaled in such a way the minimum is equal to 1. You have always a positive eigenfunction. And
The classical case would be U equal 1.
exactly, that's the isoperimetric problem. That's the beautiful idea of Bray, yes. And what?
Is a no.
Ricci is a function here. Yes.
So the eigenfunction of minus Laplacian Ricci with gamma equal what?
Oh, sorry. Yeah, gamma is now is just this.
Okay, so
The condition is that one we have. We take the first proper rescaling of the first eigenfunction, and then you look for a isoperimetric problem. I mean,
for the sphere, what do you mean? Sorry, you were saying the 1?
well, you can just take 1. Yeah. For the sphere, you can just take 1.
That is, okay, but the Ricci of the sphere is number 0.
Which is n minus 1.
Okay. And so it's
If
exactly n minus 1.
gamma is
Okay.
0, well, if gamma is 0, you don't have the Laplacian, then it's that. Then it's U equal 1.
Yeah.
There is like that required some trials, but first you guess this is the correct power here, because when you take the second variation, this one goes with the Laplacian, and then this was you just plug a constant here and cross fingers. This is the only constant that works, and yeah. So this is the proof of of the volume comparison. Pi1 is finite, you go on the universal cover, it might not be compact, but to prove this inequality, you only need the existence of isoperimetric sets. But on the universal cover of a compact manifold, you always have existence of isoperimetric sets, even if it's a strange isoperimetric problem. And then you have Pi1 is finite. How much time do I have?
You have either 3 or 7 minutes.
Okay.
And then also, I mean, if you feel like you're finished, that's perfectly fine. You want to add something as you want.
No, but just one word on the diameter, because I'm, you see, the diameter is missing here because with this number, you can't have a uniform upper bound. Yeah, uniform, it means it will only depend on the dimension, basically. You can't, okay? But what we proved is this. If you now have a complete Riemannian manifold with n greater or equal than 3, and there exists a positive view. I mean, this function always exists whenever you have that condition. But now, in the diameter upper bound, you will be involved too, okay? Then, the diameter is less than pi times the supremum divided by the infimum of u. It's an exercise for my memory. Yes. Should be this now. Now you see, if you, I mean, this is complete. You can be unbounded from above, from below. This can be infinity. So as soon as you have an eigenfunction that is was supremum is plus infinity, was infimum is 0, this theorem becomes completely useless.
You can construct examples.
And you can construct examples. Yeah. You can construct examples.
So in the compact case,
In the compact case,
the existence of such a function implies that operator is signed.
yes. In general, also in a non-compact space. If you have such a function, it will imply that.
I even, well, it depends. I mean, there's finite depth. I mean,
What?
I'm a bit confused. So in my mind, everything in the compact case, having a positive subsolution is equivalent to being stable, or that the operator is signed.
Okay.
Here is the point that you can grow at the boundary at infinity somehow, or if the manifold is non-compact.
Yeah, this you can grow like that, right? So if the manifold is non-compact, you can grow at infinity. It cannot go to 0 at infinity. Okay. And if you have one manifold in which it happens that the first eigenfunction is unbounded or it's not detached from 0, then you can't really get anything. But if you know a priori that you have a solution that is in between 1 and 2, then.
But you mean a solution of the inequality?
Sorry, a subsolution.
Okay.
Yeah.
Okay, just to understand, the existence of such a U does not imply that the operator minus Laplacian plus Ricci has a sign on n. In this compact.
Yes.
No, it implies. Yeah. You just multiply by the usual argument. Yeah. I mean,
without without any assumption how you.
No, you do.
Perfect. Okay. Just
Fisher corporation, I guess.
Yeah. Okay.
And on the compact manifold, you have equivalence with having an equality. But here, if you have subsolutions, oh yeah, sorry, maybe I was. Yeah. And well, what is nice is that if n is equal to 3, you actually get the. So in dimension 3, you get. It's magical. you get the direct spectral generalization of Bonnet from dimension 3 on. So this is numerology. Okay, so I think I'm done. Yeah. Thank you for the attention. Is there any question?
Please. Maybe just a question about this diameter bound. Since you use this weighted volume, could you expect a weighted diameter to be finite? So I have like along geodesics, I weight U itself.
Actually, this can be also proved Yeah, actually, so we have two ways of proving this result. One is using computation along geodesics. You weight geodesics and you show that weighted geodesics cannot be so weighted minimizing geodesics cannot be too long. And you do the usual second variation. And then you get this bound. There is another way, which is the original way we wrote the proof, which also gives a different way to proving Bonnet-Meyer's theorem. If the diameter is too large, you can find a solution of a prescribed mean curvature problem in your. So if the diameter is too large, you take a small ball and a large ball that is not covering the entire manifold. You can find a prescribed mean curvature hypersurface here that cannot exist if this space is too large. So you have to minimize the perimeter minus integral of h with the correct OD on h, and if this is too large, h can be taken in such a way it verifies an inequality which contradicts its stability. It's a dual way. But then the computation along, then we realized that we could do the computation along geodesics. But this one, actually the volume bound, we don't know a proof without the isoperimetric profile.
One question. So it seems to me that from a certain constant, you can prove a result on the volume. And in fact, from another constant, you can prove the result on the diameter. And in fact, what you are really proving, that's what you just said, is that you are proving that if you have a minimizing one-dimensional object, then its weighted area, in this case length, is bounded by whatever it would be in the sphere.
Yeah.
And then one could say that, okay, the other result that you have, the one on the volume, is in fact can also be stated in the following way. If I have a minimizing n-dimensional object, which is in fact the whole thing, then its weighted thing is bounded by the one of the sphere.
Yeah.
Do you have also the in-between results? Do you see what I mean?
Yeah, probably not clearly. Like
Take in some sense, which I'm not able to define for you, take a surface that is area minimizing. Well, area. Weighted area minimizing may be something. And you put your spectral condition wherever it should be. You decide also that. Can you control its weighted area?
It's weighted. Yes. So you can give. All right, now I understand what you mean, right? Yeah, I mean, so what you're telling, correct me if it's wrong, is that basically one way to say this is pass to the weighted area, get something on the weighted area, and then go back to the original one. You're asking me if you can get like something directly at the level, maybe some better results on the level of weighted area?
No, I'm saying that you stated two results. One is for codimension 0, and one is for dimension 1.
Yes. You mean in between?
Yes.
Yeah. But the one in codimension 0 on the volume is the classical one, not the weighted one.
But maybe they get it also for the weighted volume. That was part of the question. I don't know.
Is that isoperimetric profile, the isoperimetric profile of a weighted volume form with U?
Yeah, I mean, it's a bit tricky, not to define this perimetric profile or something analogous for higher.
No, I'm not trying to define the equivalent thing. I'm just asking you if you can control in some way. So controlling the diameter is the same as controlling the weighted length of geodesics. That's kind of what you said.
So you want to control the weighted area of like a k-dimensional object.
If it makes some sense.
It makes sense, but I don't. Because now, I mean, I expected maybe you should ask like for a different condition on the curvature, because like what happens when you have geodesics or sets is that when you do the variation of geodesics, you see Ricci, but also when you do a variation of sets, you see Ricci. I don't know how to. So what happens when you do, like when you take variations of k-dimensional objects, you will get. Actually, I don't know exactly. You should get some curvature operator. So maybe if you can bound that and doing the variation meaningfully, which I don't even know how to do it meaningfully. Well, I mean, you can do it. But then if you bound what you get from the stability, probably you can. So the moral of Bonnet-Meyer's is like you can bound the term that appears in the second variation of geodesics. And really, I don't know what happens if you. But it might be.
Is there any other questions? Let's thank the speaker.